So thank you for this opportunity. I'm Giovanni Bruno, and I'm a postdoc at the Catania Astrophysical Observatory. And well, I thank not only for this opportunity, but also Brett, because he introduced many of the plots that I wanted to use as an introduction. Anyway, this is going to be a presentation of an ongoing work that I'm carrying out with people named in this slide. And the reason of this work is to try and understand what the JWST will be able to tell us about starspot temperatures, in particular when starspots are occulted. And well, this is a case that I chose a plot for HAPP11 to show that in photometry in particular, we can rely on starspot occultations to say a lot about the starspot distribution on the stellar disk and also on their sizes, or also if we have a long enough coverage in terms of time, we can also deduce something about the starspot lifetimes. But if we go in multicolor photometry and in spectroscopy, we can try and say more on the effective temperature of these starspots. And in particular, when a starspot is occulted, I am showing you an example that was studied by David Singh and collaborators. This is a starspot occultation, like a zoom in the transit for HD 189733, where HST, the Hubble Space Telescope STIS, observed an occultation, and the authors looked at the variation of the size of the occultation bump during the transit, and they related this variation to the starspot contrast spectrum. So here you see some Phoenix models with the variation in terms of bump amplitude, bump height, and you see the variation in terms of wavelength. And what is used here is this expression which enables us to kind of but ignore the starspot size for a moment, and relates the peak to the ratio between the intensity of the starspot and the one of the star at any given wavelength by referring it to the same quantity at a reference wavelength. So what we try to do with this work is to see whether the James Webb will also be able to tell us something, even if the contrast ratios, as you can see, will become lower in the infrared. The answer is yes-ish, because the work is still in progress, but the results are encouraging. In any case, the motivation is, as you can see here, that the contrast model gives you some spectral features also in the infrared, where James Webb is going to be the strongest. For example, here I'm showing you the case of an M star with different colors which relate to different starspot temperatures. And here you see different observing modes for James Webb. And the two that we selected are the NIRSpec Prism, which is great because it allows you to cover the wavelength range, which goes from 0.6 to 5.3 microns. So a very good coverage for the spectral features that I showed you. And also, the NIRCam, which is combined with a dispersed Hartmann sensor mode, which was studied and proposed by Schlaventhal in 2017, which is also great not only for the spectral coverage, which misses, unfortunately, this part, but also because it enables you to go much brighter in terms of the stars that you're studying, while with the NIRSpec Prism, you are limited to stars which are dimmer than 10.5 in K magnitude. So in a very short description, what we are doing is a round of simulations where we choose different scenarios for different stars and different planets. We simulated transmission spectrum for these stars using already available tools like Pandexo for the NIRSpec Prism, and ad hoc simulator for the NIRCam simulator, for the NIRCam scenario. And we add on top, for every transmission spectrum beam, we simulated transit, and we add on top the bump that is that corresponds to the contrast that we calculate at a given wavelength with a suitable model. And we observe that this is we observe a dependency with the mu angle, the stellar limb angle. And so we try different scenarios for that. And then once we have the simulated data, to which we add the noise that we expect for James Webb with the suitable simulators, we feed back the transit profile with a different model for the starspot bump in order to try and be a little bit independent from the model we choose. And we get back to the original contrast model. And you see here an example of the results we get and the different spot models that spot contrast models that we try to feed to the observation to see whether we can recover the initial parameters. And the results, as I was saying, are encouraging, even if we are finding some degeneracy as actually expected with the starspot size. So even if in the initial expression, the attempt was to try and get rid of the problem of the starspot temperature and size degeneracy, we actually have to use some priors that we are studying now to solve, kind of get some information in order to be able to provide some reasonable constraint, at least to this size parameter, to be able to infer finally the temperature. So this is as I said, the results are encouraging, and we submitted already this work. We are working on the referee report, and probably the part of the starspot size and temperature degeneracy is the last part we will have to address before resubmitting it. So I hope I'll be able to tell you something more soon and put the result on archive. And thank you very much.
Thank you, Giovanni. Is there any question for Giovanni? The slide, there is no, but you can ask a question also if you have. You can turn on your mic and ask. And there is a question. What's the impact of the size of spot degeneracy on the retrieve temperature?
The most difficult question.
Yes.
So the effect that we are observing is that the likelihood distribution for the starspot temperature becomes bimodal. This is something that apparently is less strong when the chosen starspot size is, so the signal here of the bump is stronger, but as you go towards lower signal to noise ratios, you see that you can get two peaks in the most likely starspot distribution, and that's not necessarily avoided by choosing an initial very strong contrast. For example, if I choose a very cool starspot, I might expect to get a better fit of a better signal for the occultation, and so to be able to better determine its temperature. But in that case, it happens sometimes still to find this bimodal distribution, with the other mode being possibly even very far away from the true value.
Thanks.